Lastly, let's talk in a little bit more detail about partial melting and magmatic differentiation. They're processes that I've mentioned because I said that ultramafic stuff becomes mafic stuff, but let's talk a little bit more detail about why that is. That's what these two processes talk about. And then we'll talk about what igneous intrusion types there are and what we call different types of igneous intrusions, bodies of solid igneous rock that formed underground, what we call them. So how do rocks melt? Well, the easy answer would be you increase the temperature, right? But that's not it. There are many other factors that can affect not only temperature, but also pressure. If you put more pressure on a rock, it stays solid more because you're sort of holding it in place really hard with that force. So lower pressure favors melting. Also, water content. The more water you have, well, if water tends to want to be a liquid, it's also that water helps these the ions and the molecular components of a melt move around a little bit. So the more water you have, the more likely it is for things to melt. Also, that mineral composition is going to matter too. As it turns out, mafic material takes a higher melting temperature than felsic materials do. And so here we have that all set up in a table. So as you increase pressure, higher melting temperature, so it stays solid more. Favoring solid is on this side, favoring liquid is on this side at lower melting temperatures. If you increase the pressure, you're more likely to be solid. If you lower the pressure, you're more likely to become liquid. That's key at divergent margins. If you have very little water, you're going to want to stay solid. If you increase that water content, you're going to help melting to happen. You're going to become a liquid. If you have more mafic stuff, that mafic stuff tends to stay solid. The felsic stuff tends to melt more because it's got a lower melting temperature. Now that's a new piece of information, that the melting temperature of felsic materials is lower than the melting temperature of mafic. Let's think about how that works at actual plate tectonic boundaries. At an ocean-continent convergent boundary, like the Nazca Plate subducting under the western coast of South America at the Andes Mountains. As that oceanic plate subducts, it's getting hotter. It's increasing the temperature and it's melting. Now, because a lot of this crust is wet, right? It was just under the ocean, and that moisture, there's some moisture in here, brought down by that subducting slab. That helps this plate to melt, and it also helps melt the surrounding rocks some more. So the water at a subduction zone is key to melting. At a divergent boundary, most of what's going on, these plates are moving apart, and that means that mantle material is free to rise up. As it rises up, there's less stuff on top of it pushing down, and that means that the pressure gets lowered. As that material rises then, as it lowers, it's going to partially melt the mantle. Remember, lower pressure means easier to melt. And so that solid mantle becomes liquid as it rises slowly. And that's what produces much of the melt at divergent boundaries. We call it decompression. Melting. So we've seen raising temperature clearly melts rocks and lowering pressure does, and adding water does. And then here's that other key that we added. Mafic minerals melt at a higher temperature than felsic minerals. Now that also means that if you are cooling a rock, that they would crystallize at higher temperatures. They turn from that liquid back into a solid, right? And so the crystallization and the melting temperatures are identical, just like the melting point of ice is the same as the freezing point of water. It's just which direction are you headed in that you're talking about that point. So what does that mean? If we are starting to melt a rock and we only melt part of it, then that magma, that liquid rock material, that liquid silicate material, will be more felsic and the remaining rock will be more mafic because you start to melt the felsic stuff first. So as long as you don't melt all of it, your new material is going to be more felsic. And that happens because minerals have different melting temperatures. So remember, we saw that. We were only partially melting the mantle due to decompression melting. So that ultramafic mantle partially melts to become mafic material. If you took a mafic rock and you only partially melted it, it would probably have an intermediate composition. And if you partially melted that, it would become felsic. Here's a diagram of that. Your original rock composition is here on the silica axis with less silica, right? You started with something mafic maybe. As you started to melt it, the melt that forms very beginning, there's only a tiny bit of it, it's going to be very high in silica. And as you melt more of the rock, it's going to become, slightly lower over time. But as long as you only melt part of the rock, the content of the melt, the silica content that is higher than the silica content of the original rock. This is partial melting at work. Now, if you melted the rock completely, that's not partial melting anymore, that's complete melting. And whatever you started with is the same as what your melted material is. So partial melting only works if you only melt part of a rock. On the other end, that was melting. This is crystallization and cooling, magmatic differentiation. If you only crystallize part of a magma, the rock that you form will be more mafic than that material, and the remaining liquid will be more felsic, sort of the reverse of partial melting. It still happens because the minerals have different melting or freezing or crystallization temperatures. But as you take that magma and you cool it, the mafic minerals are going to form first. This is behind some stratification, formation into layers of some igneous provinces, like this Palisades intrusion, which is in New York. If you went and you looked at this rock face, you would find intermediate rocks up top and mafic rocks at the bottom. And that's all because this intrusion occurred deep in Earth's past. So that magma intruded into former older rocks that used to be here, but have since eroded away, and older rocks below. And so this was magma at the time. And as it cooled slowly in this big layer, what crystallized first? Mafic materials, maybe some olivine crystals formed and augite crystals. And they're just sitting there floating in this liquid. And they very slowly started to settle. As a result, this magma differentiated into solid mafic material that settled out at the bottom and more intermediate material that eventually crystallized at the top. So that's an example of the process of magmatic differentiation. This is different crystallization temperatures as it cools. This is what controls that. The hierarchy of silicate minerals and when they crystallize during magmatic differentiation is often discussed in terms of Bowen's reaction series. More mafic minerals crystallize first at higher temperatures. More felsic minerals crystallize later at lower temperatures because of their melting or crystallization points. Either way you can say it. So the most mafic minerals would crystallize out first. If you have this stuff, enough iron and magnesium there to crystallize olivine, it's going to crystallize first. As you cool it, then pyroxene is going to, and then amphibole, and then biotite mica. This is also less polymerized. This is more polymerized. And the last thing to crystallize are going to be our felsic minerals, quartz, muscovite mica, and orthoclase feldspar or potassium feldspar. On the other limb here, Turns out that plagioclase feldspar likes to crystallize at all temperatures, but its composition changes from calcium-rich to sodium-rich as the temperature changes. And so you can understand a lot about the different rocks that form, like ultramafic rocks, or mafic, or intermediate, or felsic rocks altogether, by this Bowen's reaction series, which explains differences in temperature of formation and melting of different minerals. Overall, both of these processes are linked by the fact they change the compositions of rocks as they partially melt and partially cool or freeze. Mafic rocks partially melt to become intermediate magmas. Intermediate rocks partially melt to become felsic magmas. If those magmas only partially cool, they're going to form more mafic rocks and more felsic magmas than what they started as. Let's revisit those plate tectonic boundaries again and think about what's going on. So let's start with the spreading center. Remember we said partial melting happens there during decompression melting. So this ultramafic material partially melts. That makes mafic or basaltic magmas. If they erupt, they're lavas. In an ocean-ocean convergent boundary, what we've got going on is the mafic material partially melting. Depending on how partial it is, that magma will be more or less intermediate in composition. Because remember, the felsic material tends to melt a little easier than the mafic material does, which is going to make part of that intermediate in composition. At hot spots, it's much like the divergent boundary, where these mantle plumes are going to partially melt the surrounding material in the mantle and also the crust, and it's going to produce basaltic material as a result. During ocean continent convergent, there's so much interplay of the mafic material being subducted, the partial melting of that material and the mantle, the partial melting of the continental crust that it's over, or the magmatic differentiation that allows some of the mafic material to be left behind down here, which makes it even more felsic, the magma to be even more felsic as it nears the surface. So you can make a whole range of complex things at one of these boundaries as a result of both partial melting and magmatic differentiation. So at this point, you should be able to think about why the Hawaii hotspot would make mafic rocks and why the Yellowstone hotspot would make felsic rocks. Why is that? These are both hotspots, but this one is over oceanic crust, and this one is over continental crust. So because this starts out as more mafic, because this starts out as more felsic, because the rising magmas are mixing with different amounts of those, the rocks that result from both of these are going to be slightly different, even though the ultimate source of heat are both hotspots. So let's talk briefly about some forms of igneous intrusions here and what they look like. We call whatever large igneous bodies of rocks that we find, large being, larger than human scale, we would call plutons. Meaning that they formed underground, we think Pluto, Hades, underground, so that any of those things are going to be called plutons. Batholiths are special types of plutons that cover huge areas. They're huge in size. Sometimes, as igneous rocks, as magma intrudes into older layers, it will either cut across horizontal layers and form what we call dikes, spelled with an I, or if it intrudes along the boundaries in between some of those rock layers, they're called sills. Those are all the intrusions that we've got. We've got plutons, it's a sort of general term. Batholiths are very big ones. Dikes cut across layers, and sills cut along layers of horizontal layer rock. Once it erupts, it's no longer an intrusion, but we can still talk about some morphologies. It's a lava flow if it's this extrusive rock that's sort of flowed along Earth's surface. Pyroclastic debris or ash falls are thrown up by this. Remember, they fly through the air, and as they settle out, they can form a sort of in-between. Is it igneous? Is it sedimentary? Depends on who you ask and what processes you're thinking about. That ash can settle out, and over time, it can form a new rock. Just as a reminder, the difference between dikes is sills, and the sills run parallel to the country rock layers along that plane of weakness. And dikes cut across layers. So to figure out which one you've got, you just have to look at what way the rocks around it are tending. We can see this layering to this rock that the dike is cut across, whereas here, the layering is parallel to where that sill formed. Thanks for sticking with me through this igneous rock lecture. So we've discussed a lot of different things leading up to this. And at this point, you should know or be able to memorize at least those major types of igneous rock and how it's dependent on texture and composition, and also be able to say something about the processes of partial melting and magmatic differentiation and how it shapes the types of rocks that we find at different plate tectonic settings. Thanks for watching. See you folks next time.